Welcome to Part 2 of EESIM's System Power Tool. In Part 1, we defined the target device using a power estimator file. In this case, it was a specific Xilinx Kintex 7 FPGA. Now we will complete the design. Double-clicking to define the part, you see that the input voltage and output voltage and current have been passed into the part. I can search for parts that have the design tool available. And here's the 15046. I can design it by clicking it here. We move into the design requirements page into the DC to DC converter tool. If you want to see more detail, check the DC to DC conversion tool video. Going back to my design, you notice there's a blue design it here initially, and now it's designed. Now that we illustrated how defining a block is done with a single output converter, let's proceed with the design with a triple output converter. Connecting the inputs and outputs. You've probably noticed the design rule checker in the right-hand corner. It makes sure that logical connections are made, meaning that voltages match on a given connection, current required is less than current supplied, 80% of power in is equal to power out, and the loads do not have multiple sources. Double-clicking to define. Say I want to add an LDO. Daisy chaining it from the output here. Double-clicking to define. Selecting LDO. I'll select the Max 8516. The 8516 is defined, but notice the design rule checker has found error 1. If you daisy chain a load that exceeds your converter's load current capacity, you may have to reselect the converter. This design rule makes sure you have the proper converter selected by flagging you and forcing you to reselect the converter. The tool back calculates the power in, of course, assuming an 80% power efficiency for margin. Reselecting the part to see if the error clears will show that the converter is sized correctly. And it is. Continuing my connections. Note I am using only one output from the 3-output converter. The tool automatically uses the one connection in the drill down menu and changes the converter to a single output converter. Defining my final 2 converters. Finishing my design. I should have if I've not already saved it, so I will save it now. Next, I could go to the summary, but if I do need sequencing, I would go into sequencing. Now under sequencing, I need to add a sequencer. We had 6 rails. So let's say I just want something with 6 rails. Various interfacing and features. I want a user EEPROM. Here the Max 6870, I'll select that part. I will add the rail assignment. So I'm using sequencer 1. Now I have the group assignments, which I use in conjunction with the datasheet's power on and power off supply sequencing. I can create a simple timing diagram as a record for what I want to do in my design. Apply changes. And here's my timing diagram. I can also view the schematic. When I want to review my design, I click on the Summary tab, where I see my system power parts, a data sheet of those parts, a product page, top level schematic. I see the various converters, the ones that have a design tool available. I'm going to have the design requirements, a schematic of that, and a bill of materials. You'll see that here also. I will have the sequencer selection, timing diagram. I go back up to the top, moving to download designs. Here you have a page that allows you to download everything the tool provides, the BOM and Excel format, a PDF of the design summary. You also can get an offline version of EESIM. Now you have more than a pencil sketch of your design that you can share with your colleague. Thanks for watching a demo of Maxim Integrated System Power online tool.